Hello, hello. Yeah. Hey. Okay, we'll get started. I mean, so today originally the plan was to switch topics, so that would be also help, change up some things from what we saw last couple of lectures. But we have some content from last time, which is mostly just getting a sense of a couple of tricks that I'll discuss. But there are a lot of more tricks that people have figured out. But it'll give you a sense of what people try. Okay, so these tricks are beyond the number of hidden layers or the number of neurons and things like that. So where are we, right? So we are 9:14. So next week an assignment is due. As I said last time, the first question in this assignment is really if you can appreciate what's going on in the ants versus bees example, then you should be able to adapt it to the CIFAR 10 data. Okay, that's essentially the core idea of this first question in this assignment too. I mean, I'm not showing the assignment itself, a document, but what I'm saying is the first question at least is you have some helper code. Okay, it's exactly the answers bees, and that's actually in the examples folder. If you go to CNN, loading, but this example, the first one here, but it's also actually there's a reference to where we got that example from. It's from PyTorch's tutorials. Okay, so you can just start from there, get a feel for how you do transfer learning, basically fine tuning your model a little bit, the ResNet 18 or whatever the name of the model is, pre-trained model, fine tune it a little bit, or use it as a feature extractor. Okay, that's the assignment 2, question 1. So if you haven't done it, this should be a little bit mechanical, but the big challenge there is appreciating PyTorch. Okay, so if you might not have seen Torch before, maybe you've used NumPy. PyTorch has its own way of like a little bit difference in how you handle multidimensional arrays. And then I said, right, so it's a template. So if you get a feel for like what key commands do, key statements do, like zero out the gradients and then take a dot backward to actually compute the gradients, and then do the optimizer dot step to actually do the gradient update. So there are a few key steps that you'll see. Other than that, the for loop for training is kind of something that you must have seen before. Okay, so I would say for the first question at least you have an example. For the second question is just it is not it's just as trying to get a sense of how you want to model this problem. Okay, the problem happens to be a recommendation system problem where you want to recommend a bunch of movies. So that's the business level statement. Oh, okay, I want to recommend a bunch of movies. But how do you formulate that problem into a into a model definition where you can actually do gradient updates to the model parameters? Okay, so what do the model parameters mean? What does the model even mean? That's the interesting part, in the sense that that's where you should spend time on. So actually coding it, I think the data set that we use is has 1,000 movies, some small data set, movies and ratings of movies. It's from Movie Lens data. That's what it's called. But for the sake of doing that problem, don't be hung up on 1,000 rows and 1,000 lots of ratings and so on. You can always shrink. Let's say you want to only work with 20 movies. Like, how would you solve this problem? Because if you know how to solve the problem for 20 movies, you can probably scale it up. Obviously, there's going to be scaling related computational challenges, but that's not the issue that you're trying to solve. You're just trying to map the gradient descent ideas and PyTorch, for example. How do you use these tools that I know to solve some other optimization problem, which is a recommendation system problem? That's the so you want to kind of set up, okay, what would the loss function be? What are my model parameters? Those are things that you want to spend more time on. Okay. Anyway, so we're here, and I'll start today. We'll get through the lecture goals in a second. We'll start talking about natural language processing. Okay. In fact, today's we do have a bunch of slides, but we don't have to cover all the slides. We'll start with some lightweight models. I call them lightweight models. They're actually non-deep learning models. They are actually pretty well defined, and they're actually very useful. Like one of our PhD students in the department used one of these models in his recent paper also. So we'll look at some of the non-deep learning models and then get to some deep learning ideas for text. Okay, so that's the second part of the lecture. For the first part, we'll look at some of the tricks from last time that we did not look at. Okay. So in terms of timeline, this probably is an interesting problem working with CNNs and recommendation systems. And then next time you'll work with translating text, translating from one language to the other. So that's also an interesting problem, but that's 2 weeks from now, or 3 weeks from now. Okay, with that, let me mention where we are. So we're actually trying to follow the same sequence that we have here. So we are going to work on. So we looked at some transfer learning ideas last time, and then we didn't really visualize. We were like looking at some debugging ideas. There are some practical models. I don't think I spent much time on it, but ResNet is the one that you'll use in assignment 2. Okay, ResNet is something you can easily download. If you can install Torch Vision as a package, you can get Torch Vision.models. You can just get the pre-trained model. This is a model that's trained on this as well as the other one. They're just models trained on the ImageNet data, which is like a 1,000 class one. Okay. But in terms of sequence, we are trying to get into text. Okay, just trying to get a sense of what's different for text and how do people think of they come up with new words. It's a slightly it's a related field, but it's not exactly the same as vision. So they have their own terminology to discuss ideas, right? So we'll do that. Okay, this time. I do have a quick comment on projects. So I don't know. I actually before projects, 2 students have not yet formed a group. So if they can just match with each other, that will be good. Okay, you did. So maybe you should remove your names from there and just put it on top. Okay, that's great. So because remind me, I think I need to group you guys in Blackboard as well, because everybody else has been grouped on Blackboard, but I need to group you two as well. Yeah, so I was mentioning about project. I just wanted to give a quick reminder on the project aspect. This course is actually project driven, where if you have some ideas, then obviously you can pursue it. Obviously, talk to me. We do also have Son who can help. Son, who's my PhD student, he can also help kind of formulate, ideate, refine things. If you have not yet figured out a project, I suggest looking at this project notebook. It's just a discussion of, okay, what will you be evaluated on? But I would say, it's a project is a little bit open-ended. Not everybody will do the same thing. So obviously the evaluation just depends on how much hard work you put in and what is the interesting aspects you're trying out in your project. Okay, there's no measure of, okay, if your accuracy is X%, you're off, then your accuracy is Y%, you're good. That's not the way we'll evaluate. Okay, so I would say here, definitely when you're thinking of projects, don't think of performance measures or increasing performance measures as the key work that you're going to do. It's more about getting into a domain, remember, right? So whatever domain, like let's say you're interested in finance, in healthcare, or something else, try to see if that's your interest, try to pick up a data set and try to build a model that we'll see in the class. Okay, so obviously so far we've only seen vision models. Today and next time, today we'll see some text, but you'll see that text has a lot of parallels with time series, and time series models are pretty abundant in health and finance, for example, right? So you literally have a time series of stock prices, for example. So you can pick any models. You don't have to be gravitating towards the first model that we saw, first or 1 or 2 models that we saw. There are other models that we'll cover in the lecture. Okay. Yeah, one last thing I wanted to say about projects is, try to ideate early. I actually have a couple of ideas as well. So if, especially PhD students, if you want to discuss with me, you should, maybe during the break, at least the PhD students in the audience, we can just have a quick chat if you want to just hear my suggestions out, and then we can see if that's something that you want to work on. Okay. Yeah, right. So this is the fun part of the course. I mean, the assignments are just to kind of get up to speed with, okay, this is PyTorch, how do I use it? How do I do X or Y? But it's mostly the project which is going to be the interesting part. Okay. yeah, so as I said, PhD students especially, please talk to me during the break. At least I'll write down your emails so that I can communicate with you later. So let me then come to the goals. So today's goal is point 3 of the previous lecture, which is some engineering tricks that we'll see. I call it engineering. When I say engineering, I'm not saying anything bad here. It's more, I'm saying these are all empirical driven observations which lead to some good gains, okay, while training or while model performance or whatever, right? So there are some ideas that have worked out really well, and it's good to kind of know them. But those are not the only ideas. There are many ideas in this area, but we'll see a couple of interesting ones. So that's point 3. So we'll, by the end of today's session, or by the end of at least the first part, you'll know what dropout is, what batch normalization is, and what data augmentation is. Those are the 3 things that we'll see. Okay. But the actual goal for today is for lecture 4. Just get an exposure to what are elements of natural language processing, right? So in natural language, basically we are trying to work with something which is not numeric from the get-go. At least images, they are just if you think of it naively, so they are actually just numbers, right? In pixels, the red whatever channel, the blue channel, and the green channel, they're just a bunch of numbers arranged in a certain way, right? They're already starting with numbers. Whereas text is not numbers, okay? Text is not numbers, so how do you kind of work? At least you need to do that conversion from actual text to at least some numeric representation. Okay, that's where I guess the biggest delta is. Otherwise, once you get to numbers, then many of the ideas that you already know, you can always employ. So, so just a brief introduction to natural language elements or natural language processing, as in like the keywords and ideas there. There's actually a full-fledged course. Some of you might be taking it or might take it. We'll look at a couple of, as I said, non-deep learning approaches. There are some shortcomings for every method, right, including deep learning methods. So we'll see a couple of them: naive-Bayes and latent visual allocation, for example, are 2 names that we'll see, 2 examples that we'll see. Naive-Bayes, especially if you've done ML 101 type of course, you might have seen naive-Bayes model before. So it'll be a recap for some of you. We'll actually see an interesting idea, which is you can actually even use CNNs for processing text data. Okay, so that's where creativity came in. So some creative researcher have found, okay, maybe I can just use a CNN type of architecture to actually even still process text data. So how do they do that? That's one interesting thing that we'll see. And then finally, we'll look at the idea of what are called embeddings, or vector representations of words. And there was an interesting work by researchers from Google. It's called Word2Vec. It's about 10 years old now, so we'll look at that. Okay, so of course, there are many improvements since then, but Word2Vec is just a canonical example of how to represent words or textual information as numbers, okay, either vectors, matrices, or whatever. Okay, so that's the goal. That's the second part of today's session. Any questions here? Okay. If there are no questions, yeah. So let me jump to where we left off last time. So last time we were actually looking at transfer learning. We saw some content from the slides, which was fixed feature extraction and fine tuning. But we also saw an idea called low rank approximation, LoRa, to fine tune. Okay, so we went through the code of like how do you originally have an original weight matrices or whatever, like parameters. You don't change them, especially if you have a weight matrix. You can actually say, okay, I'm gonna fine tune by not touching the original weights, but tacking on extra low rank outer products of tall matrices and wide matrices. Okay, so that way you can kind of achieve what you want, like change in weights. Okay? Because fine tuning is all about changing in weights. You just want to in the LoRa idea, we don't change the original weights, but add some extra matrix, but that matrix happens to be low rank. Why low rank? Because if you keep it low rank, the number of parameters is small. Okay, and that way you can just work with smaller number of parameters. That's the whole idea there. Okay, But that was about tuning and fine tuning. And so what we'll come back to is, in general, some ideas that can help training neural networks. In general, what happens is the moment you have deep networks, unless you use some of the tricks that you see today and maybe other tricks, it's kind of hard to train them. Okay, maybe it's built in the model definition, some extra aspects, and we'll see that in the later architectures. They may help train them a little bit easily, but if you just naively stack on, like say 10 column layers, or naively stack on a bunch of feed-forward layers, it's a little bit hard to train them. Okay, hard in the sense that you may be seeing some flat line, and then like you don't know whether that's the best performance you can get, or it's just because you're like at the wrong local optima and you're not able to get out of it because of initialization or training choices and so on. Okay, so so the first idea here is okay. So let me categorize the ideas. One idea is about is related to the data itself, and the second couple of ideas are related to the model. Okay, actually, one idea is related to data. This initialization idea is actually related to the optimization approach, so that actually should be an optimization point here. And then model specific details, specific ideas are batch normalization and dropout. Okay. So anyway, I'll explain all these keywords that you're seeing in the slide. They are empirically validated, and that's why I guess I was referring to them as engineering. So they're actually like you try out, test them, they actually work, and that's why we're talking about it. And they also evolve over time. So sometimes people find that okay, we don't need these ideas anymore because of simpler, newer model definitions and newer model architectures. When I say architecture, I'm just referring to this collection of building blocks like layers, feed-forward layers, and column layers, and so on. So we'll still stick with gradient descent based ideas. So actually, within the gradient descent family, the first order family, I think you might have seen SGD last time. I think when I was looking at the code, when I was showing the code, there was the word SGD. There was also the word Adam, perhaps. So there are choices there, even within the first order techniques. First order just means you're using gradient information to make progress. There are a lot of choices just for optimization. We are just kind of ignoring that optimization piece in today's discussion. Okay. So you can add that also as a way to do better training. And I think last time we also saw some LR scheduler or learning rate scheduler, which just means that, for example, one simple idea is, okay, maybe you should reduce the learning rate, the scale, the alpha in your gradient update as you do more and more training, because perhaps you are already at some bottom of some local optima, and so you don't want to jump around too much. Okay, so but there are many such ideas. So let's look at concretely a couple of them. So even before getting into the idea of data augmentation, there are many other things about data which may influence your work. First of all, what is its quality, right? So far we've been talking about supervised learning problems. Okay, so which means that you care about label quality, and images, perhaps the images themselves also should be high quality, right? So especially label quality is important, and there are actually new startups which are just focused on label quality and label management, and not just for classification. For example, other problems that I might have mentioned, like object detection or localization, you have to check whether the bounding boxes are in the right places and so on. Okay, so there's a lot of work that goes into ensuring high quality data. Okay? And second thing, for example, you will be reading images from disk. Then, like, is it just going to be a hard disk, a flash drive? Is going to be some object storage, technology like S3? I don't know how many of you have heard of Amazon S3 and equivalents in other cloud providers. So they're all storages which have been optimized for reading and writing patterns. And is that storage enough? Does it serve your needs? Okay, for example, maybe you want to read 100 images per second, or maybe 1,000 images per second from disk, from whatever the storage location is. Does it even support that, right? So there are many non-modeling aspects that also influence your work. Okay. Yeah. So let's actually just focus on one idea that's very applicable, definitely applicable for images very naturally, that you'll see. The idea is about augmenting data. Augmenting data just means increasing my data size. Okay, so if I had 100 examples, I can instead now I have 1,000 examples. So how did I grow by 10x, right? So I have to do something with the original data. So that's the idea here. We know that, if you have an xi example, then this just yi is passed to the loss and xi goes through your model, and then you compare them. The idea is, if you had this original data point, then maybe I can make multiple copies of it where the x can be changed. Okay, so where I can change x, but I change x. Like if you think of a feature vector, what does it mean to change x? I just change the coordinates of change some feature coordinates of it. For images, there's a very natural way to change x to some other image x tilde, and if you change it, maybe the label is the same, and therefore now you've got a new data point. Okay, so instead of the original, not instead, but in addition to the original xi-yi pair, you have maybe a new, not just a new, but several new data points. Okay, so what are the transformations? Actually, there are a lot of technical names here, but and I'm not shown here. But if you look at literature, there are a lot of names. But it's all about just knowing that if there is an object in an image, let's say especially for classification, then certain types of changes don't influence the class. Okay? So for example, cropping, sometimes flipping the image, sometimes scaling, not just in the horizontal and vertical directions, but other directions, sharing. There are many types of changes you can do while you can retain the original label. Okay, so this is an example of augmentation, and yeah, and this is exactly what you want to achieve through one of the steps I mentioned last time, which we said we'll talk about it next week. If I don't want to open up the code because there's too much context switch, but if you recall, I said there's data set object and the data loader object that you create. So when you create them, you can pass in a bunch of transforms. Okay, so these transforms are exactly these transforms. Okay, so you're just saying you can just define those transforms beforehand and make it a part of the data set object, and then therefore the part of the data loader object. When you load, let's say 10 images from data, so from disk, those 10 images, each one can be transformed in various ways and then actually gets passed into the model because you define the transforms at the beginning. Okay, and you'll see that in the example code in your assignment question 1. When you look at the example code, you'll see that. Okay. In fact, there's an interesting transform that we also do, which is which is apply, recenter the images. Okay, so what do I mean by recentering the images? So the images all, just remember there are a bunch of numbers. You will see actually in the example code that there is a bunch of like 6 numbers that recenter the image. Okay, it's not exactly recentering, but like some renormalizing the image. Okay, what is the renormalization? It's just that ResNet 18 and stuff that you'll use in your assignment, they are trained on ImageNet data. Okay, so there the typical images have certain types of numbers. Okay, certain scale of numbers and so on. If you want to apply that same model to, let's say, ANTS versus Bs, or let's say CIFAR10 image statistics. When I mean image statistics, I just mean like median pixel value and intensity, and for example things like that, they would be different. So to correct for that, any new image, you can try to recenter it or renormalize it so that it looks like an ImageNet type of image. Okay? That's just one way to kind of make the image which is out of domain, that is in your domain, similar to the ImageNet image. Okay, so you'll see that also in transforms when you define the transforms. But that was a little bit of a tangent about recentering. Here, transforms are all about changing your x to x tilde so that they still have the same label, and so you can use the data. You can augment your data. Okay, increase the data set size. At test time, as in when you want to do inference, not just test time. When you want to do inference, also you can augment your data, which basically means, okay, at test time I got an image. It doesn't matter whether you augment the data while training. Okay, that's kind of independent. Let's say you have a model and you got an image. You don't have to pass the image once through your model to kind of get the class, right? You can always do hundreds of transformations and say, especially if let's say you're searching for a car or let's say a cat, you don't know where the cat is. Maybe you could crop the image to maybe the top left and then pass it through. Maybe that's where the cat is, and you can actually detect the cat. But if you give the full image, maybe there are other noisy signals that are kind of reducing the probability of detecting a cat. Right? We saw that with the occlusion, right? So that when we were occluding the tire of a vehicle, we were we were decreasing the probability of the tire, but then there was other parts of the car which are also influencing the probability of tire in the debugging discussion we had last week, right? So only thing is, I mean, there are many ways to do it. This is just one example for ResNet, which won the ImageNet competition in 2015. Not the same size. In your assignment, you'll be working with a smaller version, ResNet 18, but ResNet 50, I think, is the full version. That won right 8 years ago. So that had, their strategy was, given an input image, they're gonna scale the image first of all to many different sizes, and then they'll get 10 different crops, certain size crops. Crops just mean like a part of the image, and then you actually do inference on all of them, and then somehow aggregate the classes. So you run each of the cropped image through your model, you get a class. In fact, you get a full probability distribution of classes. Then you can do a majority voting or whatever, some sort of aggregation of these predictions to get the actual class you're going to predict. Okay. Any questions here? Okay, so this is a very natural trick to do. I mean, other things, they're all in the same category: contrast, color. You know, you can mix all these mix all these transformations. Like you can translate the image, it's just shifting. And so, in fact, you can specify a bunch of transformations. And so, when your data loader loads that batch or a specific image in that batch, you could have multiple of these transformations, one after the other. Okay. In fact, there's some interesting research project you can also do here, which we'll discuss. If somebody is interested, we can talk during the break what you can do here. But people have been trying to figure out how to improve their data set, right? So you can't just beyond obviously collecting more data and then annotating them. You can actually rely on some tricks to really improve your performance, model performance. Yeah, and some, if you want to get some insight on why this is helpful, is exactly this, right? So it's basically adding some noise during training, and if you do the stuff that in the previous slide, you're actually averaging out the noise and you're getting a prediction. Okay? If you want to think of it as just some justification for why this makes sense. Okay, so that was about data. So we can create multiple copies of data with some perturbations, and there's still additional data points for us. Now, on the model side, we can do a couple of things. We've already seen there's a lot of choices in the modeling piece, right? So we have to choose non-linearities. We said, okay, let's just use ReLU, but you can also use sigmoid and others. Number of layers, whether it should have 3 fully connected layers versus 1 versus 5. There are a lot of choices. And filter sizes, for example, the community has converged on like 3x3, but like why 3x3, right? Why not 5x5 or 11x11? So there's some choices that we've already seen that we have to make. But what we'll see is some other ideas which make a difference in terms of a very helpful, you get a very stable training approach, so that you can actually see loss going down and it's not like all over the place. Or you can actually get good performance, as in like accuracies and so on. Remember here, with respect to simpler models, as in like non-deep learning models and deep learning models, there are two challenges. One is obviously performance, like test and train performance, the usual numbers, but also the hardness of like actually training them. I mean, you can get stuck in a local optima, and then you may give up on the model, even if the model is very rich, as in it has tons of layers. Okay, so we'll see a couple of ideas. We'll look at weight initialization, just a commentary on weight initialization, and then we'll actually look at batch normalization and dropout. Okay? Those are the two ideas. So weight initialization is just a comment that it's a very important, I mean, at least it used to be very important consideration for a lot of work that went into understanding how should we initialize weights. For example, W is equal to 0 may be bad. Okay, I'm not saying that it is bad, but it may be bad because of W is getting multiplied with some incoming whatever activations or inputs. So 0 may not be a good choice. And you can think about it why. If it's 0, then do the gradients actually propagate back? You can check that. one of the things is like, okay, I initialize weights. They obviously where you initialize, when you initialize weights, the question is initialization just means that you start from here or there or somewhere else, right? So initialization just means what is my starting point before I do gradient descent. Okay? That's okay. If you start from some unlucky position, you may get to a bad local minima. That's one thing. But it's also the question of, are you able to make are you able to make gains? Also depends on the current gradient magnitudes that are achieved, we compute by backdrop, and numbers. Basically, it's not just because I start from here, I will get there, is not always given, because you have so many other things going on, which is am I even able to get the gradient computations correctly, and whether I'm able to make progress, the trajectory. It could be that your learning rate is small, or you're in such a, it's not always going to be smooth like this. It could be like quite hilly. Actually, some people try to visualize the last surface of neural network, and it's very messy and hard because there's a million plus dimensions. I mean, last time when we looked at the MNIST data, the simple 2 or 3 linear layer model had 2 point something million parameters. Okay, so you can't really visualize that. One thing is the trajectory also, the intermediate gradients and the intermediate iterates, where they are kind of are important. Okay? So it's not a nice hill on which you just roll and you get to the local minima. It's like really, if you look at the terrain of some place, let's say, in the world, visualize the most, hard terrain. That's how it is actually. Okay. So anyway, there are some heuristics that some people have discovered a few years ago, maybe 5-6 years ago, that they have tried and they've used successfully. I don't want to name them because I haven't personally tried that, but you can search. Like, for example, if you, for example, use Gaussian, random variables, realizations from Gaussian distribution to initialize your weights, then what should be its variance, for example? So should it just be 0, 1, 0 mean unit variance, a Gaussian from which you're going to get a sample to initialize your Wij? Let's say one weight of your weight matrix, or should you use 0, 10 as your Gaussian, distribution, right? So there's some scaling behavior that people have exhaustively tried and figured it out. Okay, so that's what I mean by some heuristics that people have figured out. Okay, and doesn't even have to be Gaussian. It could be other uniform distributions or other distributions that people have tried to investigate. Okay, that's just a comment on weight initialization. We'll not talk too much about it because actually, most of the course we are sidestepping the optimization related concerns, although that is a big concern in this field. Weight initialization is one thing, but the optimization approach, the SGD versus ADAM versus RMS prop versus something else, there are many names for these gradient-based techniques, and we'll not look at them because we want to keep it focused on the model and laws and other aspects of the problems. So let's look at the second trick, second idea, which is called batch normalization. So this is it's not about initialization, it's not about data. It's some modification in the model definition. Okay, so let's say you came up with a model which was like con layer, and then pooling, and then let's say fully connected layer. You're now going to edit that and add some extra computation in between, somewhere in that computation graph. Okay, so you can think of this as an extra layer if you want. So that's what we're trying to do. And why do you want to do it is exactly because of this gradient descent issue with deep networks, because of the loss surface being super hilly, super jagged with all sorts of cliffs and stuff, to kind of improve that navigation. Okay, so the moment you introduce extra things, obviously the loss surface is going to change. Okay, it's not going to be the exact same terrain. So what is the extra stuff, right? That we want to ensure that these intermediate vectors that we're computing, intermediate tensors, or like tensors, let's say, tensors that we're computing, the numbers in them are always recentered before they go forward. Okay, that's what we want to do. Recentered in the sense that remember the z-score normalization, or even some sort of normalization that you would do, feature normalization that you would do, right? That's essentially what we're trying to do. So after every layers computation, which is after the last nonlinearity that we're applying, max of 0, x, we got a bunch of numbers, the activation vector or the activation tensor, and then we want to recenter those numbers. That's what we want to do. Okay. How do we synthesize the numbers? We have to kind of take some sense of, get some sense of mean, some sense of variance, and then subtract the mean and divide by the variance. But where do we get those mean and variances is the key idea here. Okay. And why are we recentering? It's just to influence the gradient propagation. If numbers are, think of every stage. If the numbers look, if you just look at the histogram of numbers, they all look, like nicely Gaussian distributed. That means that probably, there's definitely not going to be dead pathways, and there's going to be, gradient flows back and forth. Okay. So what's the idea? As I said, we have to do some recentering of numbers. Okay. So the way we do it is we will essentially, we're not really making them explicitly Gaussian, but we're basically just subtracting mean and some variance from every activation vector. So every set of activations. Let me just say that. So what do I mean by that? Remember, in our training, we start with a batch of inputs. Okay, let's say batch of inputs just mean batch of images or batch of just feature vectors, whatever they are. We get a batch, and then we are doing a forward pass generally, right? So what we're going to do is on the left side is an illustration of the batch of the batch, where each row corresponds to either the feature vector itself or some activation corresponding to that feature vector. So each row corresponds to an example. Okay, so if my batch has 64 examples in it, then the number of rows in this matrix is 64. This matrix is just an illustration; it doesn't have a matrix. But and then what I'm laying out in terms of columns is the activations. It could be activation vector itself if it's a fully connected layer, or it could be that tensor which I've vectorized. Okay, if it's not a fully connected layer but a common layer. Okay? It's just the collection of. So it's just each column here just corresponds to one neuron. One neuron, same neuron, different outputs because it's different inputs of the batch. Okay, so each column corresponds to that. And so what we're doing is basically for that neuron, for that batch, these are the numbers that the neuron produced, and we're just gonna recenter that for that neuron. The statistics that we see, maybe all the numbers are negative. Okay, we don't want that. We don't want that neuron to propagate a bunch of outputs where all the numbers are off in some sense, maybe all negative, maybe all positive, or something like that. So what you're going to do is just look at the neuron's outputs over the batch, subtract the mean of those numbers, and divide by the square root of the variance of those numbers. Okay, it's just the same, it's just a heuristic. So that's what we're doing. That's how we recenter it. Because after we do this and this operation, these numbers are going to be roughly between 2 to 2. If the scales were like -10 to -20, they're all going to be recentered by the mean. So maybe they become between -5 to 5, and then you have rescaling here. So maybe they'll get rescaled to some numbers between close to 0, but maybe magnitude 1 or 2, like something like a Gaussian, basically becoming a unit Gaussian. Okay, and the gamma and beta are just extra parameters. You could ignore them in the first pass. But if you wanted tunable parameters here in this computation step also, then you can add an extra parameter. Okay, extra parameters. So those two Greek letters just corresponds to extra parameters, but you can ignore them if you want. Okay. Any question here? So this is just a idea that people figured out to kind of see, so that their activation statistics. The activation statistics, all these numbers, histograms of these numbers that are produced after each layer, they kind of look nice enough. Nice enough just means, look like unit Gaussians or so on. Okay. So at test time, when you pass an image, if this batch normalization exists, then you don't know what numbers to put in here, right? So there's no batch. I mean, first of all, at test time, maybe you only send one input. But because you trained with this batch idea, you may be off, right, in terms of numbers, because at test time, if the batch part, you don't know the expectation variance, what numbers to substitute here, right? So PyTorch and other packages actually let you remember what did you do when you train, so that those numbers can be used as plugins when you actually run the model in the test mode or inference mode. Okay, so these packages help you with that behind the scenes. Okay, so pictorially, what happens then? If this was the original network, all we're doing is this is one version of where to introduce batch norm as well. So we are introducing batch norm between the con layer and before the nonlinear operation, but it's not necessary you do it this way. You could just say con includes the nonlinearity, and then I'm doing the batch normalization as well. Okay, so whichever, there are multiple patterns people have used. So here I'm just showing one pattern, but that's how you introduce. So somewhere along that pathway, you have to kind of manipulate or transform your activation vectors or activation tensors. Okay, that's all. Any questions? Okay, so what the point of doing this is that it improves gradient flows. It at least empirically observed improves gradient flows, and so that your whole process is a little bit less sensitive to initialization. Okay. But obviously, it has changed the model definition, so it's now a new loss surface with respect to parameters. Okay, so that was the previous idea. Let's look at one last idea before we stop these. Before we switch over to something else. So this idea is about a very interesting way to regularize. Okay, this is something that we have not seen before in other models, but it naturally makes sense for these network type of architectures. This is a way to regularize firstly, and how does it work? While training, every time we do a forward pass, which means that every time you get a batch, we're doing a forward pass in your model to get the last value, right, and then do a backward propagation. Every time you want to do a forward pass, this was the original network. What we'll do is we'll randomly delete some neurons. Deleting the neurons is the same as saying, okay, it doesn't matter what the neuron outputted, but wherever it's, next layer, whatever activation number I'm passing forward, I'm just going to set it as 0. Okay, that's essentially what it means. So I'm going to delete some neurons and then compute my usual scores, and then do a log transformation if I'm doing classification, and then usual cross entropy. So everything is the same, except I'm going to delete a bunch of neurons, as in drop a bunch of neurons with some probability. So the probability is now a parameter, some number that I get to choose. Let's say 25% of the time, 50% of the time, and that's how I'm going to do training. Okay, that's just the mechanical process of doing dropout. Okay. Any questions about the mechanical process? So every time I do the forward pass, remember, if I have a data set of 1,000 examples, and if my batch size is 10, then I'm doing 100 forward passes in that epoch, right? So I'll get 10, do a forward pass, another 10, I'll do a forward pass. So each time I'm doing a forward pass with 10 examples, I'm dropping arbitrarily, different subsets of neurons every time. Okay. So I drop them, I compute the loss, and then I backward propagate. If they're zeros, they're not part of the network anymore. Okay, so that's the mechanical process. So what's the intuition, right? The intuition is, if you drop a bunch of neurons, then you have a smaller network, smaller in terms of number of neurons. If you really think of network as like, how do you quantify one network is big and one network is small? Number of neurons, right? So, or especially for free-power network, it's very intuitive to say that. So how do you reduce the capacity? You drop a bunch of, if you reduce the number of neurons, it's a smaller capacity network. Okay, it could be deeper, but it may have lesser number of neurons, right? So basically, with the dropout, we're making use of smaller capacity of the network every time instead of the full capacity of the network. So we are kind of restricting the capacity or richness of the model. That's what regularization does. One of the effects of regularization is to reduce the richness of your model class. Okay, when you do L2 regularization, let's say in linear regression, your model class is a set of all linear functions. But if you do L2 regularization, you're kind of restricting yourself to a smaller, you're preferring models which have, whatever, 2 norms to be closer to 0, for example, right? So that's like a restriction. Instead of the model family being all models, now you're kind of restricting the models to be, okay, only these types of models with L2 norm small, right? So it's essentially a very similar idea. If you had all neurons, that function or that model can express many different. So the function is going to be very rich in the sense that it can express complex patterns, as in it can produce complex patterns. But if you restrict by dropping neurons, then that's a kind of a new function which is less expressive, in the sense it can only draw some other certain smaller number of patterns. Okay. So the second point is intuition is that you're forcing all the neurons to be useful. Okay? So if you drop some neurons, then some other neurons have to detect that same pattern, so that to be able to classify well as well. So you are kind of making it robust in some sense by ensuring that multiple neurons are able to get the same signal for doing the classification, right? There are many ways to also think about this, other ways, but it's just a way to kind of intuit like this mechanical process of dropping neurons while doing forward passes. Yeah, like one of the ways to think about it is you're subsampling a part of the network for each example. So you're subsampling a part of the network. If you're thinking of it that way, then basically we have you can think of it as an ensemble of neural networks that are sharing parameters. You can really think of this as, because I dropped out every time, which means I have different networks because different neurons have dropped. At test time, you can think of it as like somehow ensembling all these neurons while making a prediction. It's just an interpretation. If you want to have more intuition about how dropout can help, right? Generally high probability, which means to drop a lot, that means you are strongly regularizing, right? So if you drop 90% of the network, then the remaining 10% has to, whichever 10% survives in every forward pass, has to kind of do well on the prediction. So it's a very strong regularization. That's like saying my L2 regularization coefficient is like really big. Okay? At test time, what you can do is very similar to previously, right? So at test time, what you can do is you may not want to do dropout anymore. You can actually scale, but you still have to deal with the fact that the numbers are now, if you don't do dropout, the numbers are going to be scaled up. Okay, so you'll have to multiply numbers with the probability of dropout. So that's some extra detail, and I wrote it here. But this is just a way to rescale the numbers. Okay, if you don't want to do dropout at test time, obviously you can do many passes at test time, and then nothing changes. Yeah. Of the neurons, yeah. Yeah, we will. No, we want to make the, so when we drop 90% neurons, we will lose information. So we are hoping that the remaining 10% of neurons, we learn the parameters such that they are still able to detect some pattern. And this choice of 90 versus 50 versus 20 is your choice. But some choice is needed to kind of induce that redundancy into the network, right? So because you're making the network redundant, remaining 10% should still be able to classify. Because you're making it redundant, you're also reducing the expressivity of the network. Sorry, expressivity, yeah, of the network. So it's a choice. I mean, you can actually literally, I don't know if there's no assignment question on this, but basically you can look at impact of dropout on model. Like the model is going to be less expressive, so it might increase in terms of losses. You may see higher losses. Yeah. Yeah.
Is there dropout of a neuron limited to just one propagation or for the whole network?
Every neuron has a probability of being dropped out with some probability p.
But is it limited to just one propagation or for all the epochs?
So think of there are many ways to define an epoch. So for us, we agree that, let's say an epoch is one full pass over the data. Okay. So in one epoch, if we have, let's say 1,000 examples in a data set and our batch size is 10, then we have 100 iterations, 100 batches that we'll sample essentially. Okay. We're going to do a dropout in every one of these 100 batches that we sample. And it's not the same dropout, it will be different
That's also
neurons. Yeah. So we'll randomly flip a coin and say, okay, this neuron is not going to be present this time. Yeah. And we'll do that for every batch, basically. Every batch of data. So 100 times in that. So in one epoch, whatever the number of batches we sample, those many times we'll do the dropout. And we could be doing multi-epoch training also, so that's extra. Okay, so those are the three ideas, which is data augmentation, batch normalization, and dropout. We also saw a brief comment on initialization, but those were the three. Those are not the only three. Those are just examples of three ideas that people have used and tried. Weight initialization also, people have tried different initialization strategies. And there's references you can look into if you want to really use those initialization ideas. But then more you'll see. Actually, model enhancements, for example, there's an idea called attention mechanism. We'll see that next lecture. And then 2 lectures from now, we'll also see something called layer normalization instead of batch normalization. So they're all ideas. They're not complicated. I mean, the first time you say it, maybe they look complicated, but they are all ideas that came from people playing around and trying out training these neural networks, and then thinking of, okay, maybe how do I actually improve my training, stability or other things, capacity, constraining capacity, and so on. Because instead of dropout, you could say, okay, why don't I just add an L2 regularization on the weights of every layer, every linear layer, for example, that I have. You could do that, and then it's not necessary that you have to introduce dropout, use dropout, but it was introduced, and it was a nice way to control the capacity of the network, and it's specific to neural networks. That's why I'm mentioning it here. Yeah. Okay, so with that, let's actually switch to. Yeah, I mean, I don't want to get into the summary because we didn't cover much of it here today. Yeah, what we saw is just the last slide of the summary, because the previous 2 slides are from last week. We had data augmentation, initialization, batch norm, and dropout. Right. What we skipped is optimization details. That's where I said SGD versus ADAM versus RMS prop, some names that you might have come across. So that's something also to revisit, but we will not spend time on it, at least for now. If we have time, we'll get back to it. Okay. Let's actually switch to the next lecture, and at least I'll motivate NLP, and then we can probably take a break. Okay, and one last comment before we get into NLP is this is actually a best paper from 2017. Sure, it's a few years from now, a few years ago. So CVPR stands for Computer Vision and Pattern Recognition. It's the #1 conference in vision. That's where all these models get, all the things that you're seeing, like stable diffusion models, for example, of today, all of them have some versions that were published in this venue. But anyway, this is an example of one of the best papers from a few years ago. It's called densely connected conn networks. Okay, so what does it do? Beyond the conn network that we've seen, is basically the tensors that they're computing after every conn stage, like a tensor that compute, that's being passed not just the next layer, but also all the subsequent layers after it. Okay, so let's say if there are 1, 2, 3, 4, 5, there are 5 layers, or let's say 6 layers. Then the tensor that was computed after the first conn layer, for example, is being passed to not just the next layer, but also one hop, this layer, the other layer, and the other layer. Obviously, there are some details about how do you pass tensors, which could be of different sizes. How do you pass it to the future layer, right? So because these output tensors depend on the number of filters you choose, number of filters and the stride and all that, some extra parameters. So there is some extra stuff that they need to do to ensure that tensors can be processed nicely even if they're passed forward, and that's called densely connected conn network. Okay, densely connected because of this n times n-1 connections instead of just n-1 connections. Any comments? Like this is a key innovation. How did they find this? They found that this is actually performing better. On multiple data sets. CIFAR 100 is an example of a data set. We are actually working with CIFAR 10 in our assignment 2. Obviously, we're not at the scale of these guys yet, but what I'm saying is, sometimes simple ideas can actually move the field quite a bit, right? Just like availability of GPUs helped neural networks quite a bit in 2012 for the ImageNet competition, right? Any questions about this? So we've already seen like a few examples of good networks. ResNet 18 that you'll use in assignment is an ImageNet winner from 2015. AlexNet we have already seen, at least discussed before, and then For example, this one does that. There are other networks that are available in Torch Vision package, which I'm not even mentioning, but it's worth looking at what those models, pre-trained models do. So you don't even have to train them. You just want to get a sense of, okay, in what situation should I use them? For example, the efficient net is the name of the model. There are many such networks. Okay. So let's actually then jump into do a context switch. So now we are not going to talk about vision for at least today, this lecture. We're going to talk about language. So this order of topics is just first we'll just introduce very brief commentary on what is NLP. I mean, it's a full-fledged course in many departments, including our department, but we'll briefly introduce some comments on NLP, and then we'll start looking at some other models that that are famous, that are not deep learning models, but they're kind of useful tools to know if you have not seen them before. We'll just go through their forward passes, essentially, their model definitions. And then if we have time, we'll talk about the idea of embeddings of words, which is the basic idea of, okay, words themselves are just not numbers, so we need to get numbers from words. How do you get them? And so embeddings just mean vectors. So we create vectors of words. And that's why there's a particular name that was used by the paper from Google 10 years ago. It's called Word2Vec. So natural language concerns with all aspects of natural human languages, and we'll obviously sample a very small, narrow set of topics in this area. So for us, basically, how do you deal with text, right? So textual information, it's a sequence of symbols, right? So symbol T followed by symbol E followed by symbol X. So how do you work with this sequence of symbols? Is you can do many things, maybe not at the character level, but maybe at the word level you can do some one-hot encoding. For us, these words could be just categorical values. So we have a huge collection of categorical values, and you can just one-hot encode them depending on your application. That would be the nicest thing to do, easiest thing to do. And there are obviously other ideas that some of you have done 572 or 575, might have heard of TF-IDF and some corrections like that, some engineering ideas like that, which from which you can create feature vectors. But we'll see some ideas like that, and also see the word embeddings idea for deep learning. So some examples, just like for images, we can do translation. So machine translation, even before the recent surge of popularity on language models, which are able to generate new text. For example, here it's just about translation, going from one sentence in one language to another sentence in another language. Right. So here at least there are two languages, but you could have multiple languages, multiple languages. There's also another type of application called question answering. It makes sense for many applications, law or research work, for example. So you may have text, or even financial statements. You may have a bunch of text documents, and you can ask questions based on for which there are so there are parts of the text which answer that question, and the model's problem is to surface that answer. Okay. You could do it in a supervised learning way, where you give a bunch of paragraph, question, and where the answer is in the text pairs, those triplets, and then train a model which can, for any new text, for any new question, can generate, can say, okay, this part is the answer. Okay. Beyond the text itself, the other modality is speech, right? So speech, there is actually a lot of work here, and maybe some of you will play with it in the projects. But for example, like 2 semesters ago, one of the teams worked with OpenAI Whisper. Whisper is an automatic speech recognition model, and there are other models also. So they were working on, I guess, translation. They were working on speech recognition and then doing something else downstream. So you could do speech recognition, which is also a deep learning model. Machine translation, which these days is also a deep learning model. And then you can also go from text to speech. Okay, you can synthetically generate speech like how these virtual agents, Siri, for example, or even the navigation apps. They have like a turn here, turn there, for example, right? So they're all generated from some text, right? And you can also have some combinations like visual question answer. You can bring in multiple modalities and say, okay, given an image and then given a question in national language, answer, give us answers, right? So that is like instead of giving paragraphs and then asking a question, here it's giving an image and then asking a question. So how do you work with these types of modalities, right? Again, if you think of this problem, then what would be the training data look like? The training data would be exactly an image, a question, an answer. Okay? And given that type of triplet, a model will be learned, which for any new image, for any new question, should be able to say something about that. So now the question is, how do you represent images? Images are already numbers, and we have embeddings of images as well. You can get feature extraction stuff. Now we want to focus on this text part. Okay, how do we represent text? Text, unfortunately, is not easy. Obviously, images are also not easy. Images have a lot of issues, like occlusion, for example, of your object of interest is a typical example that people get. Here, for text, also there's a lot of challenges. For example, I saw her duck could mean this or that, right? So we don't know, right? Without extra context, we don't know. Similarly, idioms, right? So it's unclear if you're not from that, I guess, culture. If you don't understand, then you don't know what this means, right? Hit the bucket means they passed away. But how would you know that, right? How would the machine know that? Also, in terms of reference, right? This is a little bit. The ball did not fit in the box because it was too big or small. If you say big, then is the ball big or is it the box which is big? And if you say small, whether it's the ball which is small or whether it's the box which is small, right? So we can understand, but what I'm saying is these are some challenges that machines may have to face. But let's actually nonetheless move forward and actually build models, okay, which can work with text. So we'll start with simplest models first, and then look at other categories of models. Okay, let's start with some simple models. So when I say simple models, I mean in a very specific way here, which is models where we are anyway going to somehow define, given text data, we're anyway going to go into numeric land. Anyway, we're going to work with numbers, but in simpler models, we're not going to look at word-word relationships explicitly. Okay, there's a relationship between word 1 and word 2. We're not explicitly modeling or we're not capturing good relationships between words. Okay, what do I mean by that? For example, think of one-hot encoding, right? So if you one-hot encode words, and if you look at, let's say, there's like 4 words: cat, dog, house, and an airplane, and then if you one-hot encode them, since there are only 4 words, you would create a four-dimensional vector where cat would be maybe the first coordinate being 1 and all other 3 coordinates being 0 and so on. In that one-hot encoded version, the distance between cat and dog is square root 2, and the distance between cat and airplane is also square root 2. That's what I mean by some sense of word-word similarity is not being captured in that representation, the numeric representation of these words in right. So anyway, but we'll kind of spend more time on that in the next few slides. Here are some collection of models. We'll not look at all of them, but we look at. Okay, let's look at 3 or 4 of them. Okay, depending on time. So we'll start with name base. That's just a recap for some of you, and then we'll look at the others. Okay, we'll look at what they mean and how are they modeling. Any questions here? I want to ask, like, has anybody not seen any of these models? Some of these models probably are new, you have not seen, but has everybody seen a naive-Bayes model before? No. Some people have not seen it. Who's not seen naive-Bayes model on this side? You have seen it, but you want to review. That's fine. We're going to review anyway, but you have not seen a naive-Bayes? Okay. Yeah, we'll review all of them. Okay, so what is the naive-Bayes model? So what is the problem? Okay, the problem is we want to just do a binary classification of spam or not spam. Okay, or spam and ham, whichever one you may want to talk about it. So we have an email message and we want to say whether it's spam or not. Okay, so naive is a model which can let you do that classification, binary classification. And in this slide, we're directly jumping into the model definition, but I want to at least say that that's the problem. Okay, given a text, given an email, which is basically a collection of sentences, therefore a bunch of words, you want to say whether it's spam or whether it's not spam. Okay, how do you do that? You really think of it in terms of words. Okay, so given that email, the email had actually a particular sentence. Ignore the sentence structure. Just collect, first collect all these words. And let's say in your dictionary you have, for simplicity, let's say you have only 1,000 words. Okay, obviously English dictionary has a lot more. You have 1,000 words. Then what you're saying is, I got this email. I'm ignoring the sentence now. I have 1,000 words in the dictionary. Let's say it's alphabetical order, 1 to 1,000. I'm going to just look at whether, given this words in the email, which word is present or not. I'm going to create that, binary vector, okay, where a word is present and word is not present. Okay? So if the word is not present, the word in my dictionary is not present in the email, I'm going to just say, okay, it's 0 for that. So it's a very simple encoding of this email text into a vector. It's basically one hot encoding vector, except that there are multiple locations where it's 1 because there are multiple words in the email, and multiple locations it's 0 where there are no words in the email. Okay. So what I want to think in terms of a vector is because now this W1 to Wn are just the coordinates of that vector. Okay. W1 is the first word, whether it's present or not, and Wn is the last word, whether it's present or not. Okay. And what is the model now? The model description is interesting here, and it's a little bit different from many of the supervised learning models, although I said it's a classification problem, is because this model is called a generative model. Okay, just like all the generative AI stuff that's happening in the real world, this model is a generative model. Okay? So we'll kind of, I'll tell you why it's called generative model in a second. So the model is as follows. Okay, it has two statements. Okay. The first statement is that, okay, firstly, in this model, it's a generative model. In this model, everything is a random variable, okay, which means the present, so this W1 to Wn, these are random variables, which are like binary random variables. Is the word present or not, or present or not, okay. A particular example, which is particular email, is a realization of those random variables. Some word is present, some word is not present, okay. Similarly, the label of that email, whether it's a spam or not spam, is also a random variable. It's a binary random variable. It either takes a value spam or it takes a value ham or not spam. Okay. Now, since the collection of random variables, W1 to Wn, and this random variable, there is this expression here is just saying the conditional probability of all these random variables given the value of this random variable is actually, it decomposes in this way. Okay, it factorizes in this way. Okay. So if you recall, conditional probability of a random variable given another random variable, generally cannot be written this way. This representation is just a product. Okay, it's I equal 1 to n, the product of n such terms. Okay, so all you're saying is, given this random variable, W1 is independent of W2, W2 is independent of W3. I mean, all of them are independent of each other, basically. Okay. So this statement is a conditional independence statement. How many of you are lost over there? Conditional independence is all good because it's kind of needed for this discussion. So the model is making an assumption. It's a definition. It's in the model specification that, okay, we're just going to assume that words given the label are independent of each other. Okay. Next, here's the how you use the model. Okay, that's an assumption. That will lead to some estimation of parameters. What would the parameters of such a model, this name-based model, would be? The parameters are exactly this, right? So the model is making an assumption on a joint distribution between these random variables, right? So the parameters would be these types of conditional probabilities. Okay, these conditional probabilities are actually the parameters of this model. And how do you actually do given a new email, which means given an email, you'll say, okay, word 1 is present or not, word 2 is present or not. Given this realization of these random variables, you want to say what is the probability of spam. Okay? That's what a classifier would do, right? Probability of a class label given the email or given the text or given the words. Okay? We know that this is actually by, this is again since the word base, this is by base rule, you can actually write this as proportional to probability of this marginal probability of this random variable times this product form. Okay, it's just by definition of by definition. Okay, it's called base rule. So why this symbol, by the way, this means proportional to. If you wanted to write equal to, there would be a denominator. Okay, there would be a denominator which would be the joint probability of all these words only. Okay, so this random variable will not there. These would be probability of this W1, W2, W3, W4, Wn would be in the denominator. But let's ignore that because it turns out that joint probability is irrelevant. Okay, for classification, because it doesn't matter when you say probability of spam versus probability of not spam, both have the same denominator, and so you can just ignore it because your classification just depends on whether the probability of spam is greater than probability of not spam or vice versa. So when you're comparing those two numbers, if the same, if two, those two terms have the same denominator on the right hand side, you can ignore the denominator. Right? So now this is the model, and you can see that in our classification model, this could be one parameter, probability of spam. Can we compute the probability of spam using training data? We can. Can we compute the probability of each word given the class label? That also we can. So this number and this number, these are parameters of this model. Okay. Any questions about the model definition? Okay, so here's the picture of the same thing from the previous slide. But just to show what are the random variables in model. W1, W2, Wn, these are random variables. And there's another random variable spam, which is the class random variable. And given spam, these random variables are independent of each other. And that's shown, that's actually this diagram is called a Bayesian network. Okay? But it's fine. It's just a network. Network just means a graph. Okay. This graph is capturing exactly the assumption that the model is making, which is the naive assumption, which is that condition on the class, the features are independent. Condition on the class, the presence or absence of one word has nothing to do with the other word. That's why they're product like this. Okay. So that's why it's a naive assumption about independence, conditional independence, and it's a Bayesian model because we are using Bayes rule. Okay. And so this diagram is the same as the diagram on the right. Instead of like showing so many arrows, we just show one arrow, say WI is from 1 to n. That's called plate notation. There's actually a whole book by an author, Daphne Koller. I don't know how many of you know her, but she, I think, was co-founder of Coursera, I think. But anyway, she has a huge book on this called Probabilistic Graphical Model, if you're interested. Okay, so only thing left in this, so 2 slides ago, we described the model. Previous slide was just a illustration, just a diagram of the same thing. In this slide, I'm just telling you how to estimate the parameters of this model. Okay, so as I said, the parameter is either probability of, okay, the W's became X's, but just think of it as W's if you want. The probability of word, as in the probability of word being present or not present, for example, given the class, is the number of times. So in your data, you have a bunch of, in your supervised learning problem, binary classification problem, so you should have data where a bunch of examples corresponds to the spam class and a bunch of examples correspond to the non-spam class. So it's just saying probability of word being present given class spam is the number of times among the spam messages did the word occur. Okay, it's just a count of the number of times the word occurred in spam messages divided by the number of spam messages. It's a very simple, it's just counting and normalizing in your data. And then what is the probability of spam itself? The number of spam messages divided by the total number of examples in my data. Okay, that's it. These are the two estimates that you have. Okay. Given that estimate, you can always compute that Bayes rule. Given that estimate, you can just compute this and figure out whether the probability of spam is higher or probability of not spam is higher. And whichever is higher, you just say that's the class. Any questions here? So where did that words concept go? Words now just became indicator of, it just became one-hot encoding. Okay, so this indicator of word being present or not present. Okay, so the words themselves, they were not encoded in any other way. Okay? Obviously, if you have too many words, like 50,000 words or more, then that seems like a very, very challenging problem. Maybe your data doesn't even support some of the words are never seen in the training data, perhaps, but they appear in test data. So all sorts of practical considerations crop up. But this is how you encode in this model. So okay, here's another model which is actually a simple model, but has good ideas there, which is so this slide is just introducing a Markov model as a way to say is introducing a Markov model, which is also a language model. Sorry. Okay. So first of all, what is a language model? A language model, people, any model can have any adjectives. A language model is a model which can generate new words given previous words. Okay. Let's crudely define it that way. It's just a language model is a model where I can generate a new word given previous words, and then now I have 3 words. Let's say, and then I can generate the 4th word given 3 words. Now I have 4 words. Now, given the 4 words, I can generate the 5th word, and so on. Okay, so let's say if I can do that, then that would be called a language model. And a Markov model is, irrespective of NLP and all that, a Markov model is a model which obeys the Markovian property. In the sense that if any model, okay, doesn't have a natural language or anything, let's say in the finance context, a Markovian model is a model which, given its input, okay, feature vector, ignores much of the feature vector except the feature that was relevant today. If let's say the feature vector is in some sense ordered, not feature vector, sorry. Let's say the input to the model is ordered according to, let's say, time, for example. So only the most recent information matters. Only the most recent time stamped data matters. Okay, that's all Markov means. Okay, if you want to be technical, it just means that given the current timestamped data, all the data before the timestamp is conditionally independent of the tomorrow's data and all the future data. Okay, so the future data and the past data are conditionally independent, conditioned on today's data. Okay, that's what Markovian model means. So in the sense that today's data is enough to talk about future, you don't need past. Okay. Okay, let's now come back to NLP. Let's talk about a character level model. Since we've been talking about words, let's take to a switch and just talk about character. There's no big difference between a character level model and a word level model. Okay, so a character level model just means given, let's say, HEL, try to predict another L, or HELL, predict O or a space, for example, right? So it's this slide is just illustrating a character level model. So if you can build a character level language model, then you can sample a new character every time, and so you can actually start creating a sequence of characters, and maybe they look like English words. Maybe you also sample a space, and so you have like now actually a language generation model, right? So here's a simple description of a Markovian model, which satisfies which is also a language model. So first we need to choose an order for the Markovian model. Order just means whether I'm looking at 1 time step before or 2 time step before and so on. Okay, so this is just a parameter. So what do we do? So if you have data like a bunch of characters which form a word and maybe many such words, then what you can do is, given this data point, you can look at what is the probability of the letter E given letter H. What's the probability of letter L given H and E? What's the probability of letter L given L and E, and so on. Okay, I'm only looking at previous 2 letters because it's fixed order 2. But you could say order 1 would be what is the probability of E given H, what is the probability of L given E, the probability of L given L, and so on. That would be order 1. Okay, those are what we compute. So the training or the estimation of the model is just these conditional probabilities. The probability of L given HE is just the number of times LHE occur divided by number of times HE occurs. Okay, so it's just the count and normalize again, same thing as naive based. And if you have this, now basically what you have is all sorts of conditional probabilities like this. Then you can say, okay, let me start with some character. You have to start with something. So let's say I start with letter H. Then you can say, okay, actually you need to start with at least 2 characters here. So let's say I start with HE. Then you get a probability distribution over all characters, all the 26 characters, and you sample one of them. Maybe it's probability, with A, you sample an L with some probability, you sample, some other word, character with some other probability and so on. So that's how you generate text using sampling. So one of your questions, I think one sub question in your assignment 3 is actually related to this, although it's like 3 weeks away or probably more. But I just wanted to mention that it's just like counting and normalizing. So it's just an exercise in like trying to process this textual data. Again, there is no really any representation of words or characters here. It's just count statistics of, oh, did the second word, how many times the second word appeared before given the first word, or how many times the character number 2 appeared given character number 1. Okay, so it's just counting counts of things or frequency counts. That's what the model is about. So it doesn't matter what the, if you just replace all the letters by like some, shift them by 1, you kind of get the same characters, obviously, with some changes, but that's what this model is. Okay, so let's take a break now and resume at 5:05. Okay, so now we're going to switch to another model. It's called latent digital allocation. Okay, that's what the model's name is, and it's a 21-year-old model. It was proposed in 2002. Okay, but to understand that model, we'll probably want to briefly define what is a digital distribution. So digital distribution is like Gaussian distribution, like uniform distribution, like whatever exponential distribution. It's just the name of a distribution, a named distribution, which is actually a generalization of a distribution that you might have heard of. It's called the beta distribution. I don't know how many of you remember the beta distribution. It's a distribution over the interval 0 to 1. Okay, so beta 1, 1, for example, is a uniform distribution. Okay, so uniform distribution everybody has heard of, like on between 0 to 1. But if you wanted to kind of, so there's a parametric distribution with 2 parameters, beta distribution. And if you change this to, instead of 1, 1, if you make it 5, 1, you'll have a bigger bump towards the towards 0 compared to 1. And if you change its 2 parameters to 1, 5, for example, there'll be a bigger bump towards the later half of the 0 to 1 interval. Okay, so that's how you should visualize. It's flat for 1, 1, but if you increase the first parameter, then it kind of puts more mass towards the left. And if you increase the second parameter, it's more mass towards the right. Okay, that's beta distribution. Now, digital is a generalization of beta distribution to higher dimensions. Okay, in this figure, you're seeing 6 versions, 6, I guess, instantiations of this digital distribution in 3 dimensions. Okay, so how does it look like? So first of all, just like beta distribution is restricted, it's only between 0 to 1. Okay, there's no betas. So the random variable associated with the beta distribution, it only takes values up to 0 and up to 1. Okay, so nothing beyond. Similarly, digital distribution creates vectors, okay, in 3D space. Okay, creates vectors in 3D space in the sense that it's a distribution over these vectors in the 3D space, and the vectors cannot come out of this restricted region. Okay, this restricted triangular region that you're seeing in each of these plots, that's the support of this distribution. Okay, what do I mean by that, right? So first of all, this triangular region that you're seeing is actually the segment of the hyperplane, so 3-dimensional plane, okay, which is intersecting. What is a good picture? It's intersecting 3 locations on the x, y, and z axis. Those locations are 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay. It's basically like a triangle, chopped triangle that you can see. So the vectors here have a special property, right? First of all, I already told you there are 3 vectors, 3 coordinates correspond to 3 vectors, which are 1, 0, 0, 0, 0, 1, and 0, 1, 0. Those 3. These are the basis vectors, right? And the nice property would be, those vectors or any of these vectors on this triangle is that their sum of the coordinates is 1 and they're positive. Okay, obviously 1 0 0. Okay, they're non-negative. Okay, so obviously 1 0 0 0 1 0 and all of them and 0 0 1 all those three at least satisfy this constraint, right? They sum up to 1. Clearly 1 plus 0 plus 0 is 1, and they're non-negative. Okay, it turns out all these points on this triangle, on this triangular plane, this restricted part of the plane also satisfy the same property. Okay, and so Dirichlet distribution is a distribution over these vectors. Okay, so if you draw a sample from the Dirichlet distribution, you get one of these vectors on this triangle, and because it's a point on the triangle, one of these points on the triangle, it's going to satisfy the sum is equal to 1 and being non-negative property. Okay, and you can see the Dirichlet distribution itself is like a bump, right? Just like a Gaussian distribution, it's saying it's a higher probability of you draw samples from this Dirichlet distribution, you'll get points from here compared to these other regions of this triangle, this plane segment. Similarly, this one, higher probability of getting things from here compared to further away. Okay. Any questions about the Dirichlet distribution? Is everything clear about the Dirichlet distribution? Okay. Before I move on, so because I said these points on the triangle, a triangular segment or the this plane segment, they have the interesting property that they sum to 1 and are non-negative. That's exactly the property of a probability mass function, right? If you have a probability mass function, if you have a random variable which takes, let's say, 3 values, doesn't matter what the values are, but if it takes 3 values, discrete values, then there will be 3 probability numbers, right? They have to sum up to 1, right? Let's say 0.25, 0.25, 0.5. They sum up to 1. And those 3 numbers are non-negative. 0.25 and 0.25 and 0.5 are greater than 0. So it turns out this triangle, all the points on this triangle actually correspond to a this probability mass function. Okay? So every point there is a probability mass function. And Dirichlet distribution, you sample the point from the if you sample from the Dirichlet distribution, you actually get a probability mass function. Okay. Is that clear, or any questions? Okay, it's not a, as I said, by definition, all probability mass functions satisfy this constraint, and no, every point here is a probability mass function because they all sum to 1 and are non-negative. So it's the same thing. And Dirichlet distribution is a distribution over such points, and therefore, if you get a sample, you're getting one of these points, and therefore it's a probability mass function. Okay. Now, let's talk about latent Dirichlet allocation. That was just a description about Dirichlet distribution. Now, what is LDA? LDA is also a generative model. So I didn't mention too much about generative models when I was talking about naive-based classifier, but generative models are called generative models because you can, given the model specification, as in you can, if you give all the, if you define the model and all the parameters and everything is known, then you can actually generate a new data point from it, from the model description. Okay, so that's why naive-based is a generative model because given the parameters, the conditional probabilities and the spam or not, and the spam random variables parameters and all that, you can actually generate an email which would be spam-like or which would be non-spam-like. Okay, obviously the email would not look like an email because it's just presence or absence of words is what you're sampling. But all I'm saying is you can actually generate collection of words which look like spam, collection of words which look like non-spam. Okay. In the latent Dirichlet allocation case, it's the same idea. Okay, there's some generative process in the sense that given the parameter of this model, you can actually generate a document. Okay, before I jump 2 steps ahead, let's talk about what is this model's objective. This model is trying to cluster documents into essentially the model is about clustering. Okay, let me just mention that. So in particular, this model is called a topic model. What we're trying to do is, given any new document, a document is a collection of paragraphs, a paragraph a collection of sentences, a sentence is a collection of words, right? Given every document, what we want to do, what this model can do is assign that document to what are called topics. Okay, so in that sense, it's not really purely a clustering approach. So how many of you have heard of like mixed membership clustering approaches? Mixed membership just means given a data point. So remember in the classical clustering situation, given a data point, you say, hey, it's part of cluster 1 or it's part of cluster 2. Okay, you don't say, hey, given a data point, hey, 30% chance of being in cluster 1, 70% chance of being in cluster 2. You probably will not say that, but there are versions of clustering where you can have this mixed membership. Okay, so think of it, this model is closer to that version where given a document, you're just saying, okay, 30% topic 1, 70% topic 2. And what are these topics? These topics are essentially like cluster labels, and we don't predefine them. They are exactly what you think of. There could be one topic could be politics, and other topic could be religion, other topic could be sports. Okay, so topics are what you naturally interpret them of. So every document is a kind of some combination of these topics. Okay, and so but this is a completely unsupervised problem, just like clustering. Given a bunch of documents, if you fit this model, then fitting the model leads to estimating parameters of topics. Okay, and then once you have topics, any new document that you come up, you are given, you can actually put them as, okay, hey, it's 100% sports, or maybe 50% sports and 50% music, something like that. Okay? That's what the model purpose is. Okay, and it's an unsupervised model. You're not predefining, okay, these documents are this topic and this document is this topic. And in fact, topics are self-discovered in the sense that are discovered in an unsupervised way. Okay? So you have to look at, so when topics are discovered unsupervised way, you don't get the headings of these topics. You just get a collection of words, collection of words, collection of words. And in fact, not just collection of words, you'll just get the full dictionary with some weights on each of the words. And maybe if there are more weights on these types of words, you call it politics. If there are more weights on these types of words, you call it religion. More weights on these types of words, you call it sports. Okay, so you have to kind of do that interpretation yourself. Any question about the problem? It's an unsupervised, some sort of clustering problem. Okay, that's what a topic modeling problem is. How many of you have seen topic modeling before? 1, 2, 3, 4. Just 4 people. What about the others? Never heard of topic modeling? Never heard of topic modeling? Okay, that's fine. But have you heard of clustering? Okay, so who has never heard of clustering or topic modeling? Because that means you have not done ML 101, which is okay, but it's good for me to know. Okay, so what is the model? So we're gonna, so these types of models, including the naive-Bayes model, as well as this, there are multiple ways to kind of explain the model. One of the ways that I'm gonna follow is the generative approach. Okay, in the sense that we'll try to generate a document, and that pretty much specifies what the through that in that description, the model is completely defined. Okay, that's why it's a generative model. We can actually talk about creating a new document if you want, right? So the way this model works is, first of all, there's going to be a Dirichlet distribution because Dirichlet is in the name of the distribution, name of the model. Allocation is just, you can ignore it, but it's not a big deal. But there's also the word latent, and we'll talk about the word latent. But latent just means things that are not observed. Okay, what we observe is just the documents. Okay, but in the generative process, the model is going to realize some random variables which you never observe. Okay, that's why it's called a latent model. Okay, latent allocation. The word latent is there. Okay, so what is the descriptive process? What is the generative process? Generative process, by the way, it's not something complicated. It just means I'm going to realize some random variables, then I'm going to realize some other random variables given these random variables, and hopefully I'll realize my data or my data point. Okay, so let's start realizing some random variables. So firstly, we realize what is called the topic distribution random variable. Okay, so we're going to sample from a Dirichlet distribution with some parameters, alpha 1 to t. So let's say t is 3 for us, capital T is 3 for us. Okay, there are only 3 topics we care about. I mean, we get to choose how many topics we are gonna, just like in clustering, right? You need to say how many clusters you have. So let's say we have 3, t is equal to 3. So then Dirichlet has some parameters, okay, 3 parameters or whatever, 4 parameters, some 3 parameters, let's say. From there, I sample a point from the Dirichlet distribution with 3 parameters. It produces a PMF, a probability mass function. Remember from the previous slide or 2 slides ago, it produces a vector theta whose coordinates are all non-negative and they sum to 1. And there are 3 such coordinates because because we wanted 3 topics. It basically creates a probability mass function which has which is 3-dimensional in nature. Okay. So where it's just saying, okay, if you have 3 parameters with this distribution, you actually get three-dimensional probability mass function, or 3-dimensional vector here. And theta is, so what is theta? We're going to interpret theta as a distribution over 3 topics. Okay. Okay. So what are we trying to do? Remember, we are doing a generative process. We are actually trying to construct a document. And so we have to start with, oh, okay, if we're going to construct a document first, let's figure out what is the topic proportion in this document. So let's figure out, through theta, we can say if theta is, let's say 0.25, 0.5, then we can say 25% sports, 25% music, 25% politics. Okay, so that's what we are first realizing. Given that composition, we're going to actually create the document. Okay, so how are you going to create the document? Again, it's going to be an approach where word orders don't matter, very similar to name base. So, but we'll see that in a second. So then what we'll do? We are also going to predetermine that my document is only going to have capital N number of words. Okay, so we're going to predetermine that, okay, my document is going to be having 1,000 words. Then what we're going to do is for each of my words that I need to actually realize to call it a document, a realized document. First, I'm going to sample the topic of the word in the document. Okay, what I mean? So I have a 1,000-word document that I need to create. Every word in these 1,000 locations, I have 1,000 blanks currently. I need to put words there, right? Each blank, I'm going to first figure out what should be the topic of that word. Okay, so what do I do then? Because I already have theta, I'm going to say, okay, first word, which topic should it belong to? Is it sports? Is it music? Is it politics? Okay. First word, maybe it's sports. Second word, should it be sports, music, politics? Again, second word could be probably, music, so on. So here we're just associating the word, look, this word should be one from this topic. We're not even telling what the word is yet. It's a 3-step process. First step, generate the topic distribution for this document I want to generate. Second step, now since I have the topic distribution or topic composition of this document, since I want to create a 1,000-word document, each blank I'm just associating with the topic only for now. Okay, so each word can only be one of these 3 topics. Okay, according to theta. So if theta just happens to have like one of the coordinates 0, then the topic is not going to be there. Right? Right. So that's step 2. Create which topic each word belongs to. Okay, that's step 2. And then step 3 is actually sample the words given its topic. Okay, so if the first location says, okay, the topic is sports, then from the appropriate sports topic distribution, you sample the word. Okay, now what is the sports topic distribution? This is a parameter of this model, just like the alpha. This is another parameter of this model. The sports topic distribution is just think of the dictionary of whatever 50,000 words that you have. The sports topic distribution just means probability weights on each of these 50,000 words, with higher weights on the sports words and lesser weights on the non-sports words. So if you say, okay, the first word is supposed to be sports, and if you actually sample from it, more than likely you'll actually get a sports word. Obviously, with very low probability, you may get a common word, as I was saying. Okay, but more than likely you'll get a sports word. Okay. So that's how you do. So if you have a 1,000-word document, that's how you generate 1,000-word document via step 3. The step 3 variables are what we actually observe. W's are observed. These are not observed. Okay, neither is theta observed. Okay, right? And if we have a collection of documents, we only see the words, but not the topic composition or the which word belongs to which topic, obviously, right? So that's why those variables are latent variables, and that's why there's the word latent in this model definition. Okay, so what we've done is a generative description of this model. Yeah.
If you have 1,000 words and 25,
1,000 words are generated in the document. Yeah.
If it's 25, 25, 50, why do you have to set them the 12?
No, every word can be whichever topic it can be. You were saying, okay, since I know the proportion, maybe the first 25 words, first whatever 250 words are one topic and so on. Yeah, you could do that. Yeah, but here it's just the order doesn't, it's actually not going to generate any, what is called anything that makes sense. These sentences or whatever, this long collection of words. So yeah, we could, if you know theta, you could say, okay. I mean, if you do the sampling, you're just randomizing. So it may not be just because theta is 25, 25, 50 or 0.25, 0.25, 0.5 doesn't mean exactly 220, whatever, 250 words are going to be of one topic. Yeah. It could have some variation, but in terms of mean statistics, yeah, you get 25, 250 words which are of one topic and so on. Yeah.
So you said that you're generating a vector of 10,500 words and you are giving weights to, let's say, more weights to the constituted.
Yeah, that's what this extra parameter is. So remember this model, I didn't explicitly point out the parameters. Alphas are parameters and this beta, which are the distributions over dictionary words. Okay, this beta, for example, the sports topic will have basically be a probability mass function over the dictionary words, which could be 50,000 number, but there will be more weights on the words, for example, sports word compared to something else. Yeah. Yeah, so that's this. And now your question is?
I was just asking where how will you
Yeah, so these betas are the parameters that you need to learn. We are in the generative description, we never talked about learning or estimation or anything. If we had betas and alphas, this is how you generate the model, generate a document. Now what you actually have is a collection of documents, and you need to first learn the parameters. And then, if you have a new document, you have to kind of say, okay, this document is like 30% sports, 40% politics, or whatever. You need to do that is an inference step. In between, there's a learning step. And I don't think we discussed the learning step. That's the short answer, is because this is just exactly what we just discussed. So what we need to do is go from here to these parameters, at least the betas. Obviously, we also want to estimate the alphas, the digital distribution parameters. Okay, how do you go from here to here? It's a latent variable model. Ideally, what we want to do is just maximize the likelihood of the data, right? So MLE is our big hammer. We can apply MLE here. It's just that MLE is not a tractable maximization problem here, and so I don't know if people who have done 575 have heard of expectation maximization. Okay, so you'll have to do expectation maximization expectation maximization, for those who've never heard of it, is just a proxy for helping you out with dealing with maximum likelihood optimization challenges. Okay, so in expectation maximization, you do have similar latent variables. So you kind of introduce extra latent variables to make the problem easy, and then you do some maximization with that. So here you do have to do EM, and not just EM. You also do what is called variation approximation. Okay, so some extra. So these are behind the scenes details about how to estimate these things from this. But we haven't talked about variational inference yet. We will talk about it when we talk about variational autoencoders. Okay, so there's some model that we'll see 2 or 3 lectures from now, which is called a variational autoencoder, and at that time we'll talk about variational inference, the extra piece that is used in this package or in this model. But one of the pieces is expectation maximization, the other piece is variational inference. Okay, those two we have not seen in this class, and so I don't want to talk about it too much, but those are the ingredients to estimate. Okay, but if you just don't want to care about estimation, this estimation from these documents, this essentially some form of maximum likelihood. Okay, because you have the random variables, you have joint distributions between them. You can just maximize the distributions given the data, right? Maximize the parameters of the distribution that kind of explain the data the most, right? Yeah. Any other question? Yeah. I just want to say that from here to here is just maximum likelihood estimation with an extra bells and whistles. This arrow here is just MLE plus some extra behind the scenes computation. Oh, if we have parameters, we can create a document, and previously it was just a description of the model through this document creation process. If we have the parameters, generative models are able to generate something, right? That's the definition of, that's I guess in the name, right? So we just wanted to describe the model by just describing how the document is generated. That's all. I mean, the previous slide is just is like some sort of forward pass. If you want to think of it, it's like a forward pass. But in the previous slide, we assumed that we had the parameters, which means we had the betas and the alphas, and we were saying, okay, how do we generate a document? But generally, you start with a collection of documents and estimate the betas and alphas first. And once you estimate them, then maybe for a new document, you can say, okay, what is the topic composition, or other things you can answer, right? or you don't even have to have a new document. Once you have these documents, and if you can fit an LDA model, essentially doing some sort of soft clustering on these documents. So you would know that, okay, maybe 30% of my documents are talking about, sports, 40% of documents are talking about music or something like that. Yeah. And you can do it not just for, news articles, you can do other things, financial documents. You can even do it on tweets. Okay. There's some adaptation of LDA which can work on tweets, which are really short form documents, right? So what I'm saying is there's a very versatile, technique that people have been using, and able to at least make sense out of it. But in terms of word-word relationships, again, there is some relationship. Obviously, topics kind of get hopefully similar related words to have high probability mass, so you can interpret the topic. But really, there's not much. It's again some sort of statistics on counting how many times the word appeared and so on. Right, which I'm not saying that's a bad thing to do, but that's not enough, and that's where deep learning models do one more thing, which is explicitly have word-word relationships and similarities captured in the vector representations they create. Any other question? Okay, I mean, these pictures exactly say the same thing. I don't want to confuse you guys with that picture, at least. So this one is very similar to the naive Bayes. I think in the naive Bayes, I showed you some graph with like spam and then random variables below, W1 to Wn. And I showed something on the right side. That's a short form for exactly the generative process that we went through 2 slides ago. So you start with alphas, which is the parameter. Things outside this big box are the parameter. So beta is the parameter, alpha is the parameter. You start with alpha, create a topic distribution for the document, for a document. Okay. Now, given the theta, for every word that you want in the document, figure out what topic it should be. And then once you know what is the topic for each word in your document, you can sample the word itself from the appropriate topic distribution because you know which topic each word should be. Okay. This is called a plate notation. It's just a way to just show the generative process. Generative process, as I said, you have to start from something and then keep sampling random variables. That's what we did. Sample this random variable, sample these random variables, and then sample these random variables. This is what we observe, the collection of words. Okay. I mean, the generative modeling is kind of orthogonal to what data you have. Okay. You could have a generative model which can still do classification, right? Like naive Bayes is a generative model which can do classification. You have the classification data. You have emails that have spam, emails that are non-spam, but that data is not. It's just a question of how you're going to model this data that you have. Okay. So generative models and discriminative models, the only difference is discriminative models explicitly directly focus on the conditional probability of a class given features. Okay. The conditional probability of class label given features. That's what all our CNNs, speedforward networks, all of them are just trying to say what is the probability of class given input. Okay. So they're directly jumping onto that conditional probability. But generative models actually can also kind of say what that is, but they're actually finding out the joint probability in some sense between classes and the features. Right? If you remember the naive Bayes, let's actually go back to naive Bayes just to see that. Although naive Bayes is just about some conditional independence, you can actually you can actually just multiply this equation, both terms, both sides, by probability of span. Okay. If you do that, what happens? So the left-hand side is just the total of probability, right? Probability, the joint probability between all these random variables and span is equal to the probability of all these random variables given span times the probability of span. Right? That's just by definition of, if you have a bunch of random variables, you can condition in one and then bring out the term, right? So and therefore that is equal to probability of span times this product. Okay, that's exactly this term here. So what I'm going to say is that naive Bayes is modeling the joint probability between the W random variables and the span random variables implicitly. We are not explicitly calling it out, but that's why it's a generative model, because it's modeling the joint distribution of everything, and then from that you can get the conditional probability of class given inputs. Similarly for LDA, it's not doing classification, so we're not talking about this, but LDA is somehow looking at joint probability of the whole, all the random variables that we discussed. So the Z's, the W's, the thetas, it's essentially saying the whole joint distribution. Sorry, I don't know if I confused you too much about that or not. Okay, I will skip the next slide. It's just contrasting with some other model called admixture model, but we will not get into that. Okay, so we are only 20 minutes away from the end of the class, and I'm still discussing non-word embedding stuff. But I think this is an interesting application. Should I discuss it now or later? Let me see. So we have just yeah, let's actually look at the CNN model, but I'll ignore these two slides because they're talking about some baselines which are not relevant to the CNN model. So what we're going to do now is pick up a problem which is sentence classification, very similar to the spam versus non-spam. So given a sentence, we want to say it's positive or negative, like review classification, right? Or some movie sentiment classification. Think of it that way. So you have a sentence, and in fact, I think you might be doing something to do with movies in assignment 3. But coming back to this, sentence classification is just about given a sentence, one of the classes. It could be binary classification like positive or negative. It could be multi-classes as well. So so for that, we're going to use a CNN. Okay, so now you say, okay, I have a sentence and I want to classify it as a positive or negative. How can I use a CNN, right? So that's where I want to spend time on. The previous couple of slides were just talking about some baseline ideas which are not related to CNN. So we know what a CNN is, right? So at least in 2D, we know what the con layer in a CNN will do. It's basically given an input. Let's say for simplicity, it's only a matrix. Then basically CNN con layer is basically a collection of filters, and each filter convolves with the input and produces one out. Produces one matrix, 2D activation map per filter. And so if you have two filters, then you get two such maps. If you have 6 filters, you get 6 such maps. Okay, so that we know from the CNN lecture. Any question about this? No, everything good? Okay. So now let's look at. This is just talking about again CNNs. Why CNN? They capture location invariance. Remember, as we said, like if it doesn't matter where the image of the cat is, where the cat is present, but because filters can literally stride through the whole image, you can probably detect cat. And compositionality, like lower level features, filters in the lower CNN con layers, detect something, but filters at the higher layers may detect much more richer patterns. We saw this in the debugging section last time. Okay, so what we're going to do is we want to apply CNN, so we want to get a matrix first. Okay, because we saw with the previous slide, CNNs are basically at least the con layer. We have filters, and filters have to generally, at least at the minimum, work with matrices. Okay. So we want to somehow get a matrix from a sentence. So given a sentence, we want to create a matrix. Okay. How can we? So on for simplicity, let's say each row for one word in the sentence. So if a sentence has 10 words, then we want to create a 10-row matrix. Okay. But what would each row represent? Okay, that's a question. For now, let's assume that each row is just a one-hot encoded version of that word. Okay, for simplicity. Okay, so so each word is just basically a dictionary length is the number of columns, and then if whatever that word is, that location is 1 for simplicity. But we can we'll change it. In fact, the whole point of embeddings, which is after this, is to not just do one-hot encoding, right? So here is the architecture of this CNN. Okay, so let's start from left to right, and the sentence here is, I like this movie very much. Okay, and with an exclamation mark. And let's say each of these words, including let's say the exclamation mark is also, let's consider it a word. Each of these has been represented using a 5-dimensional vector. Okay. Why is it 5-dimensional? It's just for illustration purposes. You could think of it as a one-hot encoded thing if your dictionary is only this. And if your dictionary is actually 50,000 length, then it's going to be really long, really wide matrix. Okay, but let's for simplicity say if dictionary is only like or this vector is only of 5 dimensions. Okay, for each word. So now we have a matrix, right? It's just not like the image matrix, or maybe it is like the image matrix actually. Actually, it doesn't have the 3 channels, but it's still, it's a 2D object. Okay. So here in this architecture, which is actually from 2015, okay, which was published in the top conference in language processing as well, NLP. So here's the idea, right? So you start with a sentence matrix like this, and then you want to do a con layer. That's where the mystery is, right? Like what the con layer looks like. The con layer is actually just a collection of filters. Okay? 1, 2, 3, 4, 5, 6. There are 6 filters here. Okay, and the filter depth. I mean, filter depth is there's no input depth, as input depth is 1, so filter depth is 1. So there's no like what we studied in the when we're talking about con layer, and this filter width is going to be the word width. Okay, this we did not see before. Remember, it was 3 cross 3 irrespective of whether the image had like a huge width or not. Here, the width of the sentence or each word's representation here is the same as the filter width. Okay. Now, filter length, it just chose to be 4 here. It doesn't matter what the sentence is. Sentence could have like 20 words in there, doesn't matter. So here we just chose filter length to be 4. Okay. Why 4 will, just a choice, that's the only choice you get to make, which is nothing else about each filter, because the filter width is the same as the input width, and depth is because there's no depth here, there's depth is 1, right? So now this is the filter. So how do you actually slide the filter? So you start with the first 4 rows, multiply element wise, okay, come up with a number, okay, 1 number, that's this first number. Okay. You take 1 step down, which is the stride 1, do multiply element wise, get the second number. Okay. And then 1 more step down, these 4 rows, the third number, and the last 4 rows is last number. Okay, so we just try, we can't do left and right anymore, we just have to go up and down. Okay, that's the only difference. So what is this doing, right? It's just trying to see, these filters whose weights we'll learn, and basically trying to see, okay, this collection of word combinations does lead to some signal for a positive class or negative class. Okay, let's say. Okay. Similarly, there's another filter. So there are 2 filters of the same size here. So they both lead to two activation maps. Because they're going to be 1D activation maps here, basically just vectors, because the filter width is the same as the input width. Now here's a couple of other types of filters. Okay, the second set of filters have only 3 rows, and the last set of 2 filters have only 2 rows. Okay, but exactly the same operation. So these 3 row thing multiplies with 3 rows first, you get a number, and then you stride 1, multiply with 3 rows, get a second number, and so on. Okay, so at this point you have basically these activation maps, which previously it was 2D activation maps, now it's 1D activation maps, right? 1D activation map, and now we essentially got through a common operation. Okay, now it's a question of, okay, what should we do? We can just do max pool, and here's the max pool. I mean, you don't have to do it this way, but here's the max pool. Compresses 4 numbers in 1 number. How do you do that? Take a max, take an average, whatever. Right? So you got 2 numbers here, you got 2 numbers here, you got 2 numbers here, finally. And then they just concatenated them and then did a forward pass. Right? Concatenated them and just, in fact, this is a simple model where once you concatenate them, you're actually trying to predict the 2 scores. And so only 1 linear transformation. There's not even a linear layer, except for the output layer. Okay. So it's just a con layer, max pool, and output layer. Okay. Any questions about this? Why the number of rows is increasing? Here it is 4. Here it's 5.
Yeah.
That's because if it's only 3, then you have to stride more to cover the whole thing. Oh, why am I decreasing? Oh, going from 4 rows to 3 rows to 2 rows? You don't have to. I mean, this is what they proposed. right? They, but you don't have to. I mean, so this is again a good question, right? So,
I thought maybe they are writing something over.
no. I mean, the bigger filters are trying to capture if there are signals at this level. Like the filters are basically trying to look at if these 4 words have some signal for the final thing, and these ones are just looking at like are any pairs of words have some signal for the final thing. So this is very similar to the receptive field. The receptive field or the spatial field that these filters allow you to look at when for these neurons is bigger than the receptive field for these neurons is just 2 rows. Okay, but you don't have to do it this way. I mean, you can have 6 of the same size if you want. Yeah, this is just an application of what we already saw for text, except for the thing where how do you encode these? How do you go from words to these vectors? I said for now, let's talk about just one-hot encoding, but in fact, we can replace them with other encodings that we'll see in this, in a few minutes or maybe next lecture, right? That's the only thing missing. Any questions about this application of CNN? I think it's a nice application actually. I mean, you don't have to do. In fact, if you can do this, so forget about these words, right? So let's say you have time series data, which is 5-dimensional. Okay. You have a month, 30 rows for daily logs of something. Then you can actually just use a CNN if you want to go from that daily log of whatever, some length of time series data to some class. Okay? And you don't have to do a class, right? You can do other things here, but for classification, you have temporal data, some order relationship, and you can also apply CNN there as well. Okay, so the next idea is actually the key idea for this session, but we kind of missed it, or we haven't started it yet, which is the idea of embeddings. I'm going to motivate it a little bit and then we'll stop. Okay, so I mean, the motivation is basically trying to point out that the previous models are not explicitly capturing the word-word relationships that we would want to. Basically, what we want is similar words be represented similarly, right? Remember, I gave you the example that if you do one-hot encoding, the distance between cat and airplane is the same as distance between cat and dog, which is what we don't want. And to do that, we want it, we want to do that while getting these vectors for each word. So one-hot encoding is a vector for each word, right? Want to get vectors, but we want to have similar words be represented similarly. And to do that, we rely on this hypothesis, okay, which you can also. I mean, this hypothesis is just saying that we can rely on the fact that words that appear in similar contexts probably are similar in terms of semantic meaning. Okay, this is what we would like when we create vectors, and this hypothesis is saying maybe words that appear in similar contexts have shared semantic meaning. So if that's the case, then we can exploit words appearing in same context in some way to create this vector representations. Okay, and there are a couple of approaches to do that, to kind of use this idea of words that appear in similar context should have similar vectors. A couple of ways to do it, but I'll just focus on the second one. First one I don't want to get into now because of time constraint. But I want to at least motivate the second one, and we'll actually revisit this again. Okay, next time. Maybe not this slide, but so let's look at the second way of exploiting the fact that words with similar semantic meaning appear in similar contexts. Okay, that's what we want to exploit. But what is the tangible object here that we're going after? What we want is this function. Okay, I'm just calling it a W function here because at the end of the day, it's going to look like a matrix, but that's a few steps from now. So it's a function. Given words, we just want a vector representation for each word. Given a word, a vector representation for each word. Okay. For n, let's say it could be 300-dimensional, 50-dimensional, 5-dimensional that we saw in the CNN case, and so on. Basically like this, right? So word class will have a 300-dimensional vector associated with it. So every word will have a vector associated with it. But what we want is these vectors of similar words, semantically similar words, to have similar vectors in terms of. So what is similar vectors? Maybe cosine similarity, or maybe distance between the vectors, or some function like that. Okay. So how do we learn this W? This W is called an embedding, or this basically this vector representation of words are called embeddings. Okay, so it's just a new word, but basically just means the vector representation of these words. So what do? We start with, we have to learn this W, which means that W is a function which will have parameters. We want to learn the parameters. Right, we want to learn the parameters, which means we start with W with some initial values of W and do some backdrop based thing so that the parameters keep changing, and eventually what we get is a good set of parameters, therefore we get good set of embeddings or vector representations. Okay, so all I'm saying is that we can just follow an optimization process as long as we set up what is the optimization, what is the objective, what's the data, and what's the loss and all that appropriately. Then maybe by doing that we can get these embeddings as a byproduct. I mean, we actually care about the embeddings themselves. Okay, so here's an example task. Okay? Remember, we want to get good embeddings, but we don't know what the optimization process should be. So here's an example task to kind of, if we can solve this task, this predictive task in particular, then we can get good embedding. Okay? So here's an example. This is not the only task to do it, but here's an example to kind of motivate like something, some task. So what we do is train a network to classify whether an input sequence of words is a valid sequence or invalid sequence. Okay. So input sequence, we'll call it as an n-gram. Okay, let's say it's 5 gram. So n-gram is just a terminology again from the NLP community. So n-gram or 5 gram means collection of 5 words. Okay. So what do I mean here, right? So let's say we have, let's say we collect word sequences from Wikipedia. Okay. Word sequences from Wikipedia. If it's from Wikipedia, most likely those word sequences are valid sequences. Okay, I mean they're valid in the sense that they're valid in a sentence. Okay, for example, Opera's Lives Musical School or something. But then what we do is you'll take some of these valid sequences and then maybe randomly flip the third word to some random word. Okay, in the dictionary. And we know that because half these we randomly flip the words into some random words. These are not valid sequences. Okay, so now you have a sequence of words and a class which is valid, and then another kind of sequence of words, collection of sequence of words for which your label is not valid. Okay, so it looks like a binary classification problem, and what we want to do is do this binary classification problem in some way so that we actually get the W, the embeddings of words as an output as well. Okay, so here's the thing, right? So let's say this W function whose parameters we care about, which basically are the embeddings. So let's say we give the 5 words and we want to classify it as valid or invalid. So we know the label also for each input, and therefore we can compute the loss. We can do the backdrop. We'll obviously have to learn the parameters of the classifier, which is typically what we do. But in addition to the parameters of the classifier, we'll also learn the parameters of W. Okay. So those two parameters we tune so as to do well in the classification task. But as a byproduct, we got good parameters for W. Hopefully, they capture this idea of semantically similar words appear, have similar representations. Yeah. Any questions here? So what is the intuition, right? So in order to obviously do good classification, the parameters have to be good of this classifier and the W. And we'll reason about why W will have these vector representation of words that actually have similar words appear, having similar representation in the next class. But the task, I just want to point out that the task that we discussed in the previous slide is actually not the important thing. There could be other tasks, and we'll in fact see some specific tasks that Word2Vec authors from Google Research proposed 10 years ago. But the objective of that prediction problem is to obviously get a good classifier and so on, but we actually care about the W, okay? The vector representations of words. Okay. So we'll discuss the actual law, some intuition of why W would get good representations or similar representations of similar words in detail when we go over a particular implementation called Word2Vec, but there are other implementations. Glow is one, and there are many others. But if we'll talk about the reason why such an auxiliary task construction and training will get good W. But let's say we got some W. How do we analyze? Just like we did it in the debugging section of CNN, we can just visualize the embeddings of the words, right? So we can do a TSNE projection down to 2 dimensions and just look at where the words appear, right? So here is a very, you can't really read any word here, but here is a projection of those 300-dimensional vectors into 2 dimension and then replacing the point with the word. So let's actually zoom in, right? So just zoom in just to show you. So through that auxiliary training process, which is a completely random made-up thing, right? So whether the sequence of words is valid or not valid, the W was able to the W that was constructed, the vector representation of these words, they all happen to be similar because they're all close to each other in the high dimensional space, in the 300-dimensional space, and so the projection, if it's a good quality projection, actually projected them down into similar region in the 2-dimensional space. Similarly, months or years perhaps or days of the week, they're all getting projected in the same 2-dimensional space. The hope is that they're kind of similar in the high dimensional space. Okay, that's how you can infer whether your Word2Vec, sorry, not Word, any embedding that you learned is actually a decent one. Okay, there are other things that people have found, and I'll stop with that. This one, next slide, which is you can look at just nearest neighbors of some representative words to get a sense of whether your embedding is good. For example, nearest neighbor for France, just like in the previous slide, if you found nearest neighbor for Wednesday in the previous slide, you can see that all the words that were around Wednesday were probably days of week, right? So similarly, this is the nearest neighbors for some representative words in this work from 2011. Just to show you that you can assess the quality of embeddings this way. Sometimes you can also have okay, let's actually let me stop here because next page is talking about intuition, and I want to get to the intuition next time when you have higher energy levels. So any questions up to this point?
I think I understood the intuition of this, but I was just
then we'll reinforce the intuition next time.
I get the intuition of the embedding, but I don't know how the word is represented as a factor in the beginning. Is it like 1, 5, 24 letters? It's not one hot encoding. Okay. For every word, so the way we're going to do it is for every word, we're going to just, first of all, we're going to decide what's the dimensionality of the embedding, let's say 300. Although in the English dictionary, we may have 50,000 words. For every word, we're going to randomly generate a vector, which is 300 dimension in length. Okay. So it's a random vector in 300 or whatever, some arbitrarily initialized vector of length 300. And then we're going to learn the parameters. Okay, so these entries are going to be also things that we'll gradient descend on. So we'll update them and update them and update them. Hopefully they're going to be good representations. Yeah. So we'll talk about this next time. Okay, if there are no other comments, then let's pause here at least. And we'll pick up where we left off. In particular, the major thing next time will be just understanding in very specific details, at least for Word2Vec, how things work, how do we get good embeddings. And then we'll move on to sequence models, which are basically time series models, but can work with text or sequence of images or whatever you want.